It's a good time to contribute the rest of your tuition. All right, folks, the topic for today is segmentation. I'll explain it first in terms of what it means, segmentation. And let's go see what we can do about it. 1 second, page column. All right. Segmentation is a word that comes from computer vision or image processing. And what it means is that, and I'll give you a very simple meaning. There's more to it. People talk of semantic segmentation and so on and so forth. But I'll use a very simple definition. So suppose you have a hill and you have a sunrise coming out of it, right? And the usual picture, there are birds flying in the sky, and there is a river flowing here, and there is a boat in the river. There you go. Right? I guess we have all drawn such pictures when we were kids, not to mention our tree. So here's a picture. Now, when you give it, let's see how the computer sees this image. As far as the computer is concerned, computer just sees, what does it see? It just sees 3 channels, R, G, B, right? Channels. And there's an alpha channel also, but we'll leave that. And it sees basically a grid of pixels, floating point numbers, right? It just sees the height, width, and each cell, each so-called pixel, in each of the channels, let's say red channel, will contain the degree of redness on a scale, let us say from 0. It is usually from 0 to 255, but let's normalize it from 0 to 1. Right? Whichever the scale is, we can always normalize it. Let's say on a scale of 0 to 1, 1.0, from 0 to 1.0, it will have certain degree of redness. Does that make sense? The 0 would be a complete absence of red. 1 would be a complete saturation of red. So it is a number. Now the thing is, do you see that from a matrix, basically a tensor of numbers, you want to do the long journey to saying hill, hills, sunrise, birds, tree, river, boat. So look at this picture, and we want to go and say all of those things. But also, like intuitively, when we name these things, we also can tell where the hill, where, for example, the bird is or boat is. Let's take the boat. You need a location for the boat, isn't it? Are we together? So boat is here. Like if you ask a kid, they would point your finger and say, here is the boat. This is the boat. Right? And you could sort of draw it out. There are 2 ways that you could do it. And those are sort of the way we look at this whole thing. You could either say, let's say, not this. Let's say, you could say, this entire thing is the boat. You're essentially putting a mask around it, around the boat. Right? So see, what am I doing? I'm coloring it, the boat. This is your boat, let's say. Does that make sense? I've colored it. And then you could go and you could potentially color, let's say the river should be, I suppose, blue. And you could go and color the whole river blue. Now you're putting a mask around it. You're just declaring that these regions of the picture depict that. Right? And when you think of it like this, you say, aha, this to me looks like a problem in, does it look like any of the machine learning problems that you can identify? What is that? Classification. You are basically saying, given a pixel, given any pixel whose coordinates are x, y, and color channel, it belongs to which of the classes, which of the objects that you see. Now, from a catalog of objects, you identify one of those objects. Make sense? Right? Some sort of a object that you're doing. So that is one thing. But then at the pixel level, you say this is this. I'm classifying it. And some of the earlier approaches, this is literally how they went about doing it. But today, I'm not going to go historically with some of the very, very early approaches of segmentation. I'll start today with a landmark because in the interest of time, I'll just start with one of the landmark algorithms that came out. It was called the UNet. Because that algorithms, the architecture, the neural architecture is literally U-shaped. It's a very interesting architecture, U-shaped architecture. You could do that. Are we together? So this is one way of looking at it. Another way of looking at it is to say, hey, I'm going to draw the bounding box around objects. I detect objects. Right? And I'm going to put bounding boxes around the objects. Right? When you put bounding boxes, how do you recognize or what quantifies a rectangle? Well, people make some decisions right off the bat to simplify. They say you cannot make this rectangle, like this is not allowed. This rectangle is not allowed. Are we together? Why is it not allowed? So what's the difference between this rectangle and the rectangle around the board?
That has full picture of the object.
Yeah.
It's not on the flat plane.
That is right. It is not the axis, the sides and the base, they are not XY aligned. The axis aligned. So one of the simplifying assumptions that people make is, let's not make any rectangle. Let's make, and this is a rule we will use as we speak. When we speak of rectangle, a rectangle is a more generic geometric object. But in this space, in computer vision, we almost always, unless stated explicitly otherwise, we always mean it XY aligned rectangle. Are we together?
So Asif, if you go to your diagram, you only have RGB, right? How do we know the part of the board, it's not the river, right? Because how do I differentiate that the board, which is part of that's in the river, it's a different object, right? How do we draw the boundary?
No, let me try to understand or parse what you said. You want to know how do I know?
So
see,
when
the board is white
I'm looking
color.
at the river, when I'm looking at the river, if you see in the diagram, a part of the boat is inside the river, right? So I need to differentiate that it's not the water, it's a
yes, that is
object.
it. And no, that's a good problem. And that's exactly what we are going to learn. How can we train a machine to recognize these things? So I'll take you through the intellectual journey of rediscovering this whole field of segmentation. And that is a very good question to worry about. How would it know? How would a machine know?
So yes, my question is, it feels like the classification will happen multiple times, almost like training. Say you got a blue pixel from the river. Initially, it could classify that as a blue sky pixel.
Yes.
It feels like, okay, until it figures out what the other pixels are, then it's like, oh no, this is not the sky, this is actually the river.
Vasanti like made a very good point. What she's saying, and it's very crucial actually, she's saying that there is a contextual information. When I get a blue pixel, the pixels around it are informative of what it is. And if you think about it, remember, when we talk about convolutional neural networks, the convolutional neural networks have induced bias. What can somebody remind me? What are the inductive biases in a convolutionals? Convolutional. Yeah, go ahead, please.
Localization, hierarchy.
Locality, yeah. That you go from local and then you have a hierarchical structure in that. It's built into it. So there are other biases, but basically it's very sensitive to local structure. And things take on meaning from things around it, pixels around it, which is the answer to your question, that you need something that contextualizes every pixel with what is around it. Convolutional is one thing that does it. Attention in a transformer. If you remember when we talked about the transformer architecture, what does it do? Everything pays attention to everything around it. So if I were to take this picture and break it up into patches, remember, into patches, as in the visual transformer, we did the visual transformer, right? 16 by 16. So when you break it up into those patches, what do patches do? They say, what am I? Right? And then they get their meaning by observing other patches, isn't it? Right? By paying attention to other patches. And that is how it knows what it is. So as you can see, the ingredients or the building blocks of the answer to your question are in these two architectures, which is why convolutionals and attention networks or transformer networks they dominate this field. In the beginning, there were only convolutionals, but increasingly it is getting dominated with attention networks or transformer networks. And today, what I will take you through is a journey in which we'll start with a pure convolutional architecture that actually did very, very well. I'll skip some of the older ones like RCNN. Did I do RCNN last time? I gave you some idea of RCNN, isn't it, for OCR? Okay. So let's just put it this way, that so the earliest attempts to do OCR and so on and so forth and object detections were using something called recurrent CNN. The basic idea is that what does CNN do? It extracts feature maps. Do we remember? It will extract feature maps. And what are RNNs good at? They are generative. They can decode, isn't it? They can, like, for example, they can translate English to Hindi and so on and so forth. Well, transformers do it better, but in the olden days, RNNs were all that you had. And so once feature maps were extracted, the job of the recurrence network was to then decode each of those feature maps into what exactly is written there or what object it is and things like that. So those architectures with the RCNN. That's a basic idea of RCNN. I'll leave it to that. But today we'll start with UNet and we'll continue from there. But remember, guys, when you look at a picture like this, when you talk about segmentation, there are two aspects of segmentation you can look. You can say, draw me the bounding box around all the objects that you see. Or the other way, you can say, and put a mask around all the objects. Color the regions that specify a particular object. Are we together? That's so now given a rectangle, a bounding box rectangle. So the word is, so the vocabulary word that we are introducing today is bounding box. Bounding box. It's a bounding box, right? The bounding box is basically a XY aligned rectangle. Now, given a XY aligned rectangle, you can identify it by all four corners. If I give you the value of all four corners, you can tell where the box is. Are we together? Suppose I give you the coordinates of A, B, C, D. But if they are XY aligned, is there a redundancy of information here? Which of these can I get? Can I just get away with only A?
A and C.
A or C. So I can just use these two, or I could use these two, isn't it? Either of the two would give me the bounding box. And you can pick your convention, and each software libraries, they typically pick a convention. They typically pick D and B or something like that. Top left, bottom right. So that is a bounding box. Now, what are we trying to do? Let's say we are doing bounding box just for simplicity. What we are trying to say is, given a bounding box, the output is, what is it? The object that you detected. For example, bounding box 1 would be boat. Bounding box 2 could be bird. Do you see? What we want to produce is this pair of information. Would we like to do that? Right. And bounding box, and so on and so forth. Bounding box 3 would be a tree, and so forth. Now comes the question, well, how in the world are we going to train it? And I could use bounding box, I could do the mask. So the first architecture that we will learn about is the UNet architecture. UNet architecture. What this architecture does is, it takes think of an encoder-decoder. Do we remember an autoencoder? How many of us know what an autoencoder is? So few hands. What's an autoencoder?
Yeah. So basically, it will reduce the dimension.
It reduces the dimension.
Yeah.
Okay, so by the way, how many of you are registered for the Tuesday class?
Yeah, me. Yeah, I will.
Okay, so I suppose I need to go slow. So I'll step back. So before we understand UNet, we need to do encoder, decoder. So the building blocks of a UNet are encoder, decoder. It uses CNN. So the pieces are encoder uses convolution. Decoder uses what colloquially is called deconvolution, but actually is transpose, logically, transpose convolution. This is something we just taught. Those of you who did attend, remember that we just covered it in Tuesday, a little while ago. But anyway, for the benefit of those of you who are not in the class, Tuesday class, I will give a short, I can't give a whole session of that, but we'll do that. These are the ingredients. Then it also has something new, residual or skip connections. Think of it as short circuits.
VAQE.
Say that again, yeah? Variational autoencoder. No, it's just a basic autoencoder. I'm talking about a basic autoencoder here. No variation for the unit. A skip connection. Bottleneck, do we remember the word is bottleneck? Bottleneck. So these are the 4 topics I'll touch upon. Encoder, decoder, encoder uses some. So guys, have I explained convolution and deconvolution to you guys? I have, right? So that one, I'll assume that you are familiar with. Residuals, I don't think I have explained yet. It's a little advanced topic, but I'll explain that today. And then we will have all the building blocks of a unit. So let's take a digression. We'll take a little journey into this. See, when you build, so in the beginning, just think that you're building, it doesn't matter whether you're using feed forward or you're using convolution. Suppose I start with information. Information belongs to a high dimension space. Are we together? So for example, this could belong to, so if you're doing a fully connected layer, forget CNN also, fully connected, or feed forward network. What would an image look like? For example, our MNest image would look like 28 cross 28 cross. MNest is just grayscale, so one channel, isn't it? That would make it 784. 784 dimensional vector. Right? So n is equal to 784 dimensional vector. I feed that vector of 784 dimension, and then I keep creating layer after layer, deep layers, But I keep on decreasing the width of the layers. Are we together? These layers are not as deep, not as, let's say this is from 768, just for the sake of argument. Let's say I go to 512, 256, 128, 64, down to, let us say I go down to 16 dimensions, okay? 16 neurons. So this final layer, final layer of the encoder contains only 16 layers.
60 neurons.
Sorry, 16 neurons. Thank you for correcting me. I was suddenly distracted by a German friend of mine who at one time was very, so he was on the political spectrum. I suppose he was on the liberal side of it. And one day he was feeling very frustrated with what he called those country bumpkins who are on the other side of the spectrum. And he says, those people, you have to, they can only grasp concepts that can be understood by 2 neurons.
Yes.
And he was furious. Like, and somehow that mental picture is stuck in my mind. So whenever I draw autoencoder, I sometimes wonder if I need to reduce it down to 2 neuron representation. So, but what does an encoder do? Suppose you create a network like that. Now you would say, do you realize that this encoder, because it contains not just linear transformations, but it also contains deformations. Linear transformation comes from each neuron. If you just take the Z, gives you, Z is W dot X plus, right? So suppose X goes in, right? X1, X2, Xn go in, right? This is your X vector. They go in, and what happens? They all have weights, W1 to Wn, right? They get multiplied. So each of the input dimension is given a different amount of importance, different significance. How much significance to give to each weight is essentially, to each dimension of the input is the weight. Right? And B is the overall bias offset that you do. Right? So one very intuitive picture that I have is, suppose you're trying to create color for paint your wall. Right? Let's say that you paint your wall and from the shop you get only 3 colors. Let's say red, blue, green. I'll just take away sort of a simple analogy. And your job is, Z, you need to produce some color that you like by mixing up the paints. Now, what will happen? You don't want to mix them in equal proportion, isn't it? And when you do that, you control the blackness or the lightness of it. And how do you increase it? Make it more pastel by adding some white to it. You'll pour in some white on top of whatever mixture you made. Are we getting it? Right? So that's what you will do. You'll add some white here, and then you will have a differential amount of red, differential amount of blue, and differential amount of green. And then when you take it all together, this is literally your, do you notice that this, you see the intuition, how obvious the intuition is. So you're just doing a linear combination. Like, for example, let's say that you want your room to be mostly bluish, right? So what will you do? You will add more blue, less red, maybe a tinge of green, right? But certainly some white. So usually in America, genders are very color segregated. I was told, like at one point, I had 2 daughters. I have 2 daughters, actually. So then, when they were young and we're going to paint their rooms, I went to the usual Home Depot and I was looking at color choices. And the first thing the person asked me is, oh, are they boys or girls? I said, girls. And the person immediately took me to the pink section, pink and light yellow and pastel color sections. And I said, what has that to do with anything? And they said, no, these are the colors more appropriate for girls, apparently. Right? Now, we come from a different culture, of course. In our culture, in India, I suppose the only color that matters is the color that is not too expensive. So,
Even also the color that's free.
that's right. Right. So, but yes.
Religious aspects also come to play. Black.
Oh, black is not good. Yeah, that's true. That's true. Yeah, in India, like obviously, it's very odd. Actually, one thing I noticed that the interpretation of black and white are just the opposite between Indian and the Western culture, isn't it? In India, to wear complete white is a symbol of sorrow, grief, right? Whereas here, to wear complete black, I suppose, is a symbol of sorrow. And so, anyway, so these are color notation. Anyway, that's a huge digression. Let's not get there. Right? So, I remember that I was once gifted a pink shirt, a pastel pink shirt, light pink shirt, and I brought it from India and I was wearing it. And then some of my, I remember a colleague of mine doing research with me, an Italian, and he kept on looking at me, and he says, "I didn't know some things about you." The color matters a lot in this country. People interpret it. Okay, so that's we go. So I'm a little bit. Maybe I need to change my analogy, not give this picture of colors when I talk of linear transforms. But anyway, then there is an activation function at the end of it, right? What does this? Why do we need this in neural networks? Why does this keep sneaking up there every time? The deformation, for it to be a universal approximator, you need to have a deformation. It could be any sensible deformation function. Deformation, the conditions are it must be continuous. If it is monotonically increasing, not absolutely necessary, but generally a good idea. If it has, and so on and so forth. Right? There are certain properties, well-behaved properties. If it is differentiable, even better. Right? If it is not, for example, just 1 or 2 points, if it is not, that's okay. But it shouldn't be like this is not a good, for example, is this a good activation function? The one that I just drew? Probably not. Right? You don't want it to be bizarre. You just want it to be like this or like this. Relatively simple functions. And the ReLU, of course, like this, which is fine everywhere except that it has a non-differentiability at one point. But anyway, you do that. So now think of this autoencoder. Why this digression? All of these layers, at the end of it, the net result is what? It becomes a function. X goes in and some function comes out, Z comes out, which belongs to some lower dimensional space. Here, for example, 16 dimension, isn't it? And you pass this in, n was 784 dimension. Do you realize that there's a massive reduction in space? And you're saying you're taking something and projecting it down to 16 dimension. Is it necessarily true that when you compress or when you go down to lower dimensional space, you lose information? Is that true? I see a lot of bobbing heads, but no skeptics.
There is no actually, but in autoencoders, there will be latent, it will be mapped to a latent space.
Yes.
Higher
So
than
Z
the,
is your latent space. This is your D. D dimensions is your latent space. This is your latent space. Prashant. So my question is, when you take simple examples, guys, when you go from 3 dimensions to 2 dimensions, do you necessarily lose information?
usually, yes.
Distilling the information, right? Putting the code.
Right. But distillation always means you lose something. Right? When you go distill water, you're left with salt and good pure water comes out.
It also depends on the type of use case, type of information. Some cases you will, some cases you will not.
Give me an example when you don't lose information.
I would say the information itself is actually more relevant in that particular dimension.
All right, guys. I'll show you an example.
Yasif, I have a question if you don't mind.
Yes, go ahead.
So
But if
what
I
I was
do mine,
yeah, I know.
okay,
If you don't mind
then
my
you go ahead,
driving
please.
and the sound, yeah. So what I thought is if I go from 3-dimensional to 2-dimensional, and the way I think I will lose some perspective or information, but as long as it satisfies my need, 2-dimensional need, then I don't lose information. So it's in the eyes of who is looking into that. That's what I
Actually,
thought.
you're pretty close. It's a good thought. It's a good thought. And thanks for trying. We're very close, actually. Anybody else? Hint. I don't know. Maybe I need to zoom out a little bit. What am I holding? Hint, hint.
We get only a viewport of, so we get Africa or,
Okay.
or the USA.
This globe exists in how many dimensions? 3 dimensions. Imagine that there are no hills on the globe. It's a flat globe, a sphere. Right? Now tell me, if you are an ant on the sphere, can you give the location of the ant precisely with just latitude and longitude? You can give that, right? So you can also give it with a 3-dimension, XYZ, right? In a 3-dimension. So I can take XYZ and have a function that translates that XYZ to, let us say, latitude and longitude. Do I lose any information?
No.
And therefore, you realize that I went from a higher dimension to a lower dimension with 0 loss of information. It is something you should know. I'll give you another example. Suppose, the word is filled up with examples. Imagine this line. Any point here is given by xy, isn't it? But I could also, if I were a little ant here walking, I could just give one thing. What distance have I covered from one end of the line? Isn't it? I can give it with only one dimensional information. So this is a point that you have to remember, guys, that just because you reduce the dimensionality of the data does not necessarily mean that you're distilling or you're reducing the information content. It's a very common misconception. Now, generally, if you get trained in differential geometry and algebraic topology and these things, you become much more aware of it. But I thought I'll bring it to you because our entire field of machine learning, entire field is a transformation from one dimension to another, linear and nonlinear. That's what neural networks do. They take you from one space to another, one dimension space to another. But when you do that, you have to know, are you losing information or not? You see that, right? And you have to know that you're not necessarily losing information.
Does it also mean from the start you didn't dimension correctly in this case? Basically, you didn't dimension optimally.
No. Data comes to you in the way you get it, right? For example, see, any given situation, the data gatherer may give you data using whatever parameters they choose. Necessarily doesn't mean that it's relevant, or it is the best reference frame for that. In fact, the whole idea of, in many ways, when we talk in machine learning of representation learning, we say deep neural networks are representation learning machines. What does that mean? We're trying to learn the best representation of this data. We are trying to, first of all, that space, dimensional space, latent space, and that representation of this data in that space, that is optimal. It's a search for that, because if we can do that, we can have a perfect classifier, perfect regressor, whatever it is that you want to do. Optimal, not perfect, but optimal classifier, regressor, etc., that you do. So remember, this is important. And by the way, recommender systems are all based on this hypothesis. Let's see, imagine a world in which, like Amazon, how many items do they have in their catalog? Make a guess.
Billions.
The last I checked, it was in the order of 100 million, multiplied by anything from 0 to 9. 1 to 9, 100 million. How many users does Amazon have? Let's say a billion, right? A billion user. Right? My data dates back many years. It used to be 300 million. So billion now looks plausible. So any user can purchase any item potentially. So if I were to ask, given a user, what is the likelihood that the user would prefer or like some item? You could say, given a user as a vector, let's say that there's a product one, there's a shoe, there's a printer, there is a bicycle, etc., etc. You can give for this user, let's say user Joe, a certain degree of affinity for that. Right? Let's even go with the scale of -1 to 1 for the sake of argument. Right? Does this particular shoe, let us say it is a brand X shoe, right, does not like it at all. This the user doesn't care about, right? Because the user has gone completely digital, really loves outdoors. You're getting the idea, right? So the user exists in a user vector exists in a space that is the products, number of products, right? Number of products is the vector that you can associate with the liking of this user for products, isn't it? You can turn the problem the other way around and you can say, given a product, there are all of these users, isn't it? User Joe is here, Jane is here, Mike is here, and so on and so forth, right? And this particular product, let's say bicycle, will be really liked by Joe because we just saw Joe loves outdoors. Jane also likes it. Mike is a bit of a couch potato, so would not like to be in the vicinity of a bike, and so on and so forth. Right? So you can create a vector. Then again, this vector would be a billion dimension given a product. For every user in the system, you can create a number. You see, these are very high dimensional spaces, isn't it? And yet, recommender systems work on the hypothesis that you can take the Joe, you can take Joe, and you can take the bicycle, and you could both put it into a lower dimensional representation. For the sake of argument, I'll make it 2 dimensional. It's never 2 dimensions. Let's say 2 dimensional. Right? When I say 2, in reality, in real life, it may mean 200 or something like that. But let's say 2 dimensional. And here is Joe, and here is bicycle. And let's say here is Mike. So if I want to find what to recommend to Joe, a product recommendation, I can go to this embedding latent space and just pick up bicycle. Bicycle would be a good recommendation for Joe. Why? You can literally see that Joe and bicycle, when put into the same latent space, they are neighbors. They're close to each other, isn't it? And so now you see the relationship of that to an encoder. If I could have an encoder that can project both Joe, Mike, bicycle, etc., all into this 2-dimensional space, then making recommendations is easy. If I want to recommend a product to Joe, I just find all the products around Joe. If I want to recommend who to sell this bicycle to, I find all the people around that bicycle. Does that make sense? And at the end of it, guys, this is how recommender systems work. By the way, if you are wondering, how many of you use Spotify and TikTok, etc.? In a very simplified way, this is your recommender system, quite literally. This is how they work. in the latent space. Right? You find neighbors in the latent space. Right? So now I hope you realize the value of an encoder. Right? And remember that encoding doesn't necessarily lose information. But there's something you can say now, but wait a minute. If you really think about it, we can talk of something called the intrinsic dimension. You look at this line. Let me make this line a lighter colored. What color? This. If you look at this line, its intrinsic dimension is actually 1, isn't it? It just happens to live in a higher dimension, right? Likewise, the sphere that I'm holding up, this sphere, assuming there are no hills and valleys, its intrinsic dimension is 2. The surface of a sphere is 2-dimensional. And so long as I reduce it down to its intrinsic dimension, you don't lose information, isn't it? One second, John. And so comes the deep insight. In many ways, you can say that machine learning solves problems in 2 ways, 2 steps. And many machine learning problems are solved this way. First, you use complicated algorithms of whatever kind you want to find the true intrinsic dimension into which you want to project the data. And once you have projected data into that, then solving it becomes easy. Are we making sense? Right? So, for example, if I were to ask, this is spring, where is it snowing? Very easy. I go here and start all the regions near this is still snowing. And the closer I move towards the equator, the less likely that it is still snowing. Roughly speaking, right? You have a prediction model. You see how easy it is. Right? So in some sense, that's the value of representation learning. It's one instance of representation learning. We are saying, okay, let me find what it is. Recommender systems thrive on the belief, on the hypothesis, which empirically gets validated, that user and products, they have their affinity, their taste, the intrinsic dimension is way, way less than 1 billion dimensions. Are we together? Typically, it's 100, 200 or something like that. I've made it 2 here, but 100, 200. And when you do that, empirically, you can see how uncannily accurate these recommenders are these days, isn't it? They do that. Anyway, so that is about the encoder and a huge long digression into the encoder. Now, you can get, so now we realize that we can get a representation, a d-dimensional short representation. You can do it using a fully connected layer. What else can you do? You can do it using a convolutional layers. Right? What happens with convolutional layers? Anyway, how many of you have not encountered convolutions at all? All of you have encountered it. So what do convolutions do? When you move around the image, scan the image with the kernel, you are feature extracting, local features you extract. You create feature maps. Right? And if you don't pad and if you don't do things, then you do the pooling, the max pooling, min pooling, whatever pooling you do, you reduce the size of the feature map compared to the initial image, isn't it? And so you realize that your data begins to get into a smaller dimension space, right? It becomes smaller and smaller. So in both the cases, whether you use feed forward or that, you reduce the size of the data. Now, when you do that, and especially when you use convolutional neural net, what happens is that convolutional neural nets have a process that each successive layer, as you extract the feature, right, there is a give and take. The higher layers are very spatially aware. This pimple on the cheek, or the dot on the cheek, is on the cheek here. Right? As you go down through convolution after convolution, what it is extracting from that, the feature maps are doing a semantic extraction. Right? So the layers that you end up with, they have lost that little pimple on the cheek. Are we together? But what they have understood is a little bit more global semantic structure. I'm looking at a face. Are we together? That's what it has understood. So that is something to remember. And now comes the part about the decoder. Now, why in the world would you do that? Well, it's fun to do that. Right? So you get this Z, and then you feed the Z into a decoder, and this function, this was the function f of x, producing Z is equal to f of x. And then you have a decoder function, g of x, g of z, to produce x prime, g of z, of the latent. And what the decoder tries to do is it tries to sort of, in the most basic form, it tries to guess what was the picture that z represents. Are we together? Right? So one example would be, if I give you the longitude, latitude, can you therefore infer the XYZ coordinates? Right? But in a picture, if I gave you a cat and the cat became a latent representation, can you decode, or I gave you a digit, 8, can you decode it back to the shape of 8? That's what a decoder is. Now, UNet architecture is a very simple architecture, which basically says, take a picture. So take a picture, and the picture is cat. As you can see, a very well-drawn cat. It goes through an encoder decoder. It goes through. So what you do is you go through the encoding process. That's all right. Encode it to some bottleneck. You have a bottleneck. You have a latent representation. But when you decode it, right, then you choose what you want to do. Go ahead, Jay. Okay. When you decode it, now comes a trick, and this is the fun part with decoder. No, there is no requirement that you want to decode it back to the original cat. What if I choose to decode it to the mask of a cat? Right? I decode it to this picture, which is this. What is it giving me? It is telling me where in the picture is the cat, the mask of a cat. And now you say, well, wait a minute. How in the world will I train this network to do that? That seems mysterious, isn't it? You gave it a cat and you're asking this machine to give you the mask of a cat. And how can it do that? Any hints? No, what you do is, actually, there are not many ways in machine learning. In neural networks, there's only one trick. So all problems are solved with only one trick. You create a loss function and you create label data, supervised learning. Right? So what you do is, you have to give it this. You have to give it a cat, this image, and this image, somebody has to go put a mask on it. Right? So this is your X, is this. This is your ground truth Y. And then you feed it into the encoder decoder, it will come up with some gibberish. And then you say, well, that's not going to do it. Right? And so it will predict, let's say that it predicts something like, now this doesn't look like a cat at all, the mask of a cat at all, right? For example. So then you say, well, this Y hat won't do. I can create a loss function that measures how much Y hat departs from the masked cat. So you realize that you made a loss function not between the output and the original image, but you made a mask with the loss function between this and the mask. Let me call it mask. If I do that, then what happens? This machine will learn to produce masks. Well, it turns out there's a bit of subtlety here. There are ways to make it better. When people try to do that, they realize that you need a little bit more to make it work. I'll come to that. But you could have done something else, actually. Given this architecture, you could instead have said, guess what? What if I give a low resolution image, a blurry image, and ask it to produce a high resolution image? infill it. Now you say, well, that's cheating. You don't even give that information in the input. Right? You give a blurry flower, and then you say, produce for me a high res flower. This is called super resolution. Oh.
This example is the same problem. The machine doesn't know why
that is right. That is right. And so the whole question is, where did you inform it? The answer is, you didn't inform it in the forward journey, but you informed that the answer is wrong through the loss function. See, the loss is telling you that you are wrong and how wrong you are. So, and just think about it. There's actually a pretty deep implication. You are telling the machine, see, I won't show you what I want. I give you something, you produce something, and I'll tell you how wrong you are. And from how wrong you are, you figure it out. Right? Loss is just a measure of how wrong you are. And you figure it out. And the good thing with machine is that, unlike human beings who give up after 3 tries, right? Machines can go on and on and on and on for billions of tries. And finally, it will figure it out. And it will start producing the masks.
Hackathon assignment is very well.
Right. So,
also we know probably it's a many to one answer, right? Leopard and the cat may have the same answer. Like
they can have the same. Yes, it is true. It is true.
You're deliberately
doing
many
that.
to one.
Yes. Yes. And you're basically saying, if my job is to find the mask, which is the topic of the day, segmentation, then I don't give the segmentation as input. I just say, here's an image, you go produce whatever. But if you don't produce the mask that I want, I'll just tell you how wrong you are.
That's all. And
then you back propagate from that and you learn from it. Right? Likewise, I'll give you a low resolution flower, and then you better somehow fill in the details. And I'll just tell you how wrong you are. Right? So you can super resolution. Or the most widespread application of this, as you will learn, is, has anybody heard of diffusion models? DALI 2, and stable diffusion and mid-journey. How many of you have played with any of these? Or gone to just ChatGPT and said, give me a picture of something. Right? Actually, let's try. Let's see how good or bad it is today. Just for a diversion, let's go to chat. Anybody would like to go to ChatGPT and let me try that. Let's see how well it does today. Just in case you guys are worried that the singularity is coming and these machines are about to take over. Chat.
They're already there. That's singular.
Oh, we'll find out. I just want to have it, guys, I'm just trying to have a little bit of fun so you get the idea of how you train machines, guys. So we'll go there. Create a picture depicting how the UNet architecture learns. Should we try this? Let's see how well it does. And how much does it look like the actual picture in the research paper? We'll see that. So this is your DALI 2, which internally uses a UNet. Oh, this is it. Okay, now let's go and look at what the research paper looks like. Right? I'll put it on the left. And where is that? This, where is the curves? And let's go down to, so by the way, guys, are you having fun? Like, I'm trying to give you the concept of how these things work. Oh, by the way, now you know why I put this picture here. It is masks, right? So let's look at the paper itself. Research papers, UNet. I put this side by side for you guys. Yeah. So you can you can rest assured that your AI overlords are not yet here to enslave you.
One could argue that the prompt has to be given properly.
Well, try different prompts. Try whatever. What prompt would you like to give?
How jump over the
That is too easy.
Extracted from the UX.
Even that will fail. Depict a technical architecture of the UNet
give some reference to
that is used in DALI.
And drawn in the form of a research paper, like
Drawn in the form of a research paper diagram. All right, since you guys are up to it, okay, maybe AIs are ready to take over. Did you guys know that there's actually a church now formed that is already ready to yield power to the AI overlords, and and people are already saying, okay, don't kill us because we have already agreed to follow you. Well,
this is the best.
added more layers to the previous one.
It's like a Marvel comic style.
Yeah. Yeah. Well, at least it's beginning to slightly look like an encoder. All right, guys. So funs apart, let's go back to the paper, back to the main idea. So, guys, what else can you do with UNet? Here is the so with this encoder decoder. Now, this encoder decoder. Let me just stop at these two. The third thing is literally diffusion models, image generation. The architecture that you are learning today is at the heart of it. Therefore, please take it seriously. I'm giving you a very important topic, and I'm introducing you to diffusion models, which will come in the subsequent weeks. So, is it fun so far? Right? There's only one problem to it. It doesn't quite work. It's like, you guys doing the receipts project.
And the loss is very high.
Loss is very high. Right. In principle, it should have worked, but in practice, it didn't work so well. Now, this was a bit of a problem, and it was actually solved in a biomedical context. The researcher who did it, if you look at the original paper, actually, I just moved off that, or is it still open? Let me see. Yes, look at the topic of the paper, convolutional networks for biomedical image segmentation, right? For a very practical need, like they say, necessity is the mother of invention. You had to do tissue boundaries, cell boundary segmentation, right? You draw that. And so you see this, right? In this image, you had to create the masks for each of the cells. It was a real problem. So now what they did is they did something interesting. There's a traditional way in which the paper is represented, but I'll represent it in a more modern way. See, guys, each layer. So first of all, they used a convolutional layer, CNN. They use CNN. So you know that this image will become smaller and smaller and smaller image, like, feature maps, and then it will become a tiny feature map. And then you can do deconvolution, and it will become something. You will upsample it, right? You will get to higher resolution versions. You'll get to higher resolution versions of this image, right? What they did is they made a key observation, which I think is a lovely insight. What they said is that, see, if you look and pay attention to what I'm saying, because in a way, that is the heart of this paper. By the time you reach here in this journey, you are doing semantic extraction. You're creating feature maps or representation learning. Are we together? Right. So semantic. So by the time you come to this layer, you are semantically rich. But in the process, what have you lost? You have lost locational, spatial information, isn't it? So as you go down, this increases, semantic information increases, but as you go down, the spatial information was more in the reverse direction. You know, originally you had more spatial information. The pimple is right here, right? Which gradually you lose. Are we together? So now what they said, that see, if I want to discover the mask, I don't just need to say cat. I need to tell where the cat is. Or if I want to put cells, like in this particular case, tell where the cells are, I need to be spatially aware. Does that make sense? You need to be spatially aware. And I need semantic information, understanding that, yes, this is the cell, this is the cell, this is the cell, or that's a cat. You need both semantic as well as spatial information. So they thought, how will I do that? Very easy. When you go in this decoder journey, do a clever trick. At each stage, see, this information is passing on like this, isn't it? But don't just let it pass like this. Add this information also. Right? The encoder, the equivalent encoder layer, you still have it, right? You add that information also like this. Now, do you notice that my arrows are beginning to draw an inverted U? Right? And so the way they represented the paper was, they represented actually, they turned the encoder decoder into a U shape. So they said, okay, here is it, big, smaller image, smaller image, smaller image, smaller image, smaller image, and then big, bigger, 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 bigger. And what you do is you have a bypass of information. These are your residual links. Why? These things are containing more spatial, they are spatially rich, isn't it? Whereas this journey here, you know, if you go here, in this journey, what is coming through the encoder decoder's normal path? It is more the semantic learning, representation learning that is coming. This is semantically rich. And the moment they put these two thoughts together, what they came up with is one of the most successful neural architectures in computer vision.
Was that they encode during that forward pass? Provide that spatial information as well?
No. There's no such thing as a free lunch. Like if you move your filters around the image, remember that it's a process of zooming out in some sense, isn't it? Remember, the moment you do pooling, what are you doing? You're looking at the next feature extraction has a bigger field of perception. The perception field increases, right? You're zooming out a little bit, right? And as you do that, very tiny feature details are beginning to get sort of lost to understand the bigger picture. Right? So you're getting richer semantically, but you're losing spatial information, precise spatial information. That is the structure of a CNN. The convolution process is getting semantically richer.
So Asif,
At the cost of spatial information. Prashant, go ahead.
I wonder, so they have taken this analogy from the OSI layer of the network, right?
The layer 1, layer 7.
Yes.
Well, it is not inspired by that or there, but I do see where you're coming from. See, if you look at the OSI stack, physical layer is bits and bytes, right? And as you go up at the information layer, you keep adding headers to that. At the IP layer, all we can say is where is the packet coming from and where is it going and what packet it is, with the bytes and some error corrections and stuff.
The init layer, like so similar to encoder decoder, right? So the packets from application it come to the physical, and from the receiver side, they keep adding headers on each layer.
No, that is true. One way to see, one analogy you can make is that any application layer, bit of information, as it goes down into the TCP layer, for example, from the HTTP layer, HTTP adds its HTTP header. You put it onto the TCP. The TCP adds its own transmission control layers, right, which goes down to the Internet Protocol layer, which chops it up into tiny pieces. I mean, TCP itself does the windowing. But yes, there's an analogy here. And in the other end, you sort of start stripping it off.
Right? We are not kind of like.
We are not doing that. We are not doing that.
Yeah.
See, in TCP, the distinction between the OSI stack and this is, there is no learning. There is no feature learning here. It is just a dumb protocol to transmit information. That's the difference. You add more information to it. That's right. Yeah, that is right. You keep adding metadata headers to it. That is right. But yeah, I can understand where your analogy is coming from. This.
There's no extraction there.
That is right.
Layering actually meant for scalability.
Yeah.
You can't just learn. You can't know what every individual knows. And populate the routing table. So basically, you just scale it up and.
So, guys, this beauty. Do you see that this whole, the entire architecture is, when you think through it, it's a very elegant idea, isn't it? We are just taking convolution, deconvolution, and saying, hey, in the journey, I'm losing something. So why don't I concatenate it every time I go upscale it? Right? And so UNet became wildly successful. It was the king of the hill for a long, long time, and it still is. Right? For segmentation, it does very well. Now, see, what has happened over the years to conclude this thought is, people have added attention to it, or transformer-like units they are creating now. And then there are ways of doing it without the unit at all, completely. We are going to do that in the afternoon, right? Pure transformer ideas also have emerged. But unit has had a very good run. And in fact, now I'll tell you a little bit about diffusion models. Diffusions are generative models we are going to do in subsequent weeks, or may not do it. We may do it in LLM 2, time permitting, we'll see. But I'll give you a basic idea. See, what diffusion models are built up of is this thought. Suppose I have a picture of a cat. Right? What I do is, and this idea is actually so interesting that you have to pay a little bit of attention to get it. Like, it seems bizarre almost. Suppose I take this image and I add a little bit of Gaussian noise to it. You know what Gaussian noise is? Just every pixel value, just perturb it a little bit. So now my picture will get a little bit blurry. I get a blurry cat. And I do it again, and I get a blurrier cat. And then I do it n number of steps, and what do I get at the end of it? What's that?
Pixelated.
No, you don't even get any pixelated cat. There is no cat there anymore. It's disappeared. Right? You will just keep getting pure noise, isn't it? So you say that makes sense. You're just erasing by adding noise. Ultimately, what you'll be left with is nothing but noise, because at each step you're losing information. So far, so good, guys, intuitive. And now comes the thought, and it comes from, of all things, non-equilibrium thermodynamics. Right? Yes. What's up with these physicists? They always come up with weird ideas. So what they said is that, what if you could reverse this process, or train a neural network to start from noise and just conjure up a cat, right? So remember your encoder decoder, the unit thing. What if we could do train it in such a way that at each stage, I will give it a noisy image and it will go back to the previous image. Oh boy, Do you remember that's exactly what
Deconvolution.
you can do it with deconvolution? And those of you who came to the Tuesday class, did we remember doing the denoising stuff? Right? That is it. And that's exactly using. So in other words, what we can do is we can say, hey, here is a blurry image. Come up with a better, like do a super resolution or do something. Figure out what is it that I blurred? What is it that I added noise to? And you train a neural network over and over again to produce that, a unit to do that. Right? And then what happens? There's a bit more here happening here. Based on how I seed this pure noise, so that is the text seeding and so on and so forth. We'll come to that. There's a bit of transformer sitting there, but anyway, we'll come to that. Based on how I seed it, I can direct it to, all it needs to know, what this machine will know, is that when I train it on millions of images, right, what will it know? That from pure noise, it has to find its path to decode into one of those images that is meaningful. Because if it decodes into something junk, what will happen? The loss function will penalize it. Isn't it? Because what's the whole idea with all these units, etc.? I'm not telling you the answer, but if you give me the wrong answer, I'll penalize you. Right? And so you give it noise and say, create a less noisy version. And oh, oops, I don't like your answer. So here's a penalty. So by doing that, what you end up doing is you end up training a machine that will conjure up beautiful pictures out of pure noise. You see that? This is one piece of there's a little bit more going on there, but what you basically understood is, at this moment, literally the diffusion in the diffusion moment. So what you did is, you took a very good picture and you added a bit of noise. It's a process of diffusion. Right? What does it mean? Each of the things has moved from its current value. Pixels has moved from its current value. Right? You have done perturbation of it. Gaussian perturbation. And then you say, hey, machine, go decode it back to what it should be. And then you do even further and you say, well, how about now? Can you decode it now? And then you train it to do that. And then you add more noise and you say, what about now? And decode it now. And you keep on going it until you give it just random noise. And at each stage, keep on applying unit over and over and over again till it comes back with. At each stage, it will come up with a slightly better image and slightly better image and slightly better image and slightly better image till it has produced something for you. Now, the only thing missing here is the guidance through text. Like, you don't want just a something. You want this cow jumping over the moon. Are we together? So how do we bring that bit in? We will learn. But what I wanted to show you is how powerful UNet is, not just for segmentation, not just for creating super resolution. And you see the idea. In a way, this is an exercise in super resolution, isn't it? The reverse diffusion path. Yeah? Not only for this, that it has far-reaching consequences. That's why this architecture is a very important architecture. Now, guys, I will give you a task. Is it fair game to give you a task now? Let's do this. You all have your cell phones? Not with sample images on the internet. Take the cell phone, and if you were to go out, you can turn right or turn left. If you turn left, you'll come to a picnic area and a little pond. And there are ducks there. Go take a picture of the trees and the ducks in the lake, the pond, or whatever you like, picture of each other. Bring it back, bring a few pictures back. Go get UNet. Write a Jupyter notebook to create masks on that picture. Does that seem fair game? Go mask it.
Mask the ducks or what do we mask?
Just mask the ducks if you want. right? Or mask, whatever, find the masks and so forth. See how far you can go with it. Right? And answer the question, can you at all make progress with it? I don't know. I'll let you figure it out. So your job is to collectively form teams, right? Use the unit and see what can you apply to and what can you not apply to. And how far can you go? Does that seem fair game, guys?
So if you feed an image to human model, what is the expected output? Is it like
Mask.
masking or
Mask.
the
Segments, the segmentation. So guys, play with this, right? I'm not saying that this will necessarily be perfect, but play with this. If you can't, then of course you can go back to one of the classic example data sets and okay, do one thing. First, do it on the example data set, right? And then do it on something that you have taken a picture of. Is that appetizing enough to do over lunch?
So for this, the path of like the encoding and the decoding, the unit, or even for the other encoders. So the code, right, visualize the code, will be like the two blocks, right? So for two network, one is on the forward, the other one is on the backward.
Yeah.
Then there'll be like the whole training loop for both of them.
No, not for unit, for diffusion models. Forget diffusion models. I was just giving you a taste of it. We'll do it much
Not
better.
the diffusion model. I'm asking about the unit.
Yeah, unit architecture. One thing I would suggest, because it's just encoder and decoder with just residuals going back and forth. One of the things I did, now coming back to our website, guys, I give you an explanation. There's also another, I noticed there's a YouTube video also that explains it. Right? Watch this YouTube video just to get another person's perspective on how they explain it. And then there are a couple of links. Units have been very popular. So in GitHub, there's a tradition to create compilations called the awesome this, awesome that. There is an awesome unit here. As you can see, there's a vast variety of unit architectures that people have created. You can play around with that, right? Then just see the richness of it. Or rather, let me just say, you will notice that there's a lot of train test, etc., etc. You can, do you notice that model weights, you can literally get those models and play with those models if you want. And there are variations of units that you can look at. In other words, today morning, first half, gives to becoming conversant with units. Units are a powerful architecture. We need to know it. Before we replace or do some transformers into it, right? And the diffusion models, etc., become familiar with this. Then there are transformer variants people have created of the unit architecture. It is awesome units with transformers. You don't have to do it with CNNs. You can do it with transformers. People have done that. There are papers, more recent papers. And lastly, I would encourage you to read this particular thing, unit, a PyTorch implementation in 60 lines. So guys, can you please do this? As a team, sit down and deconstruct it. I will walk you through this code right now. Explain what it is. So guys, what just happened? Okay. Yeah. So look at this. Look at this block. You're convoluting input channel, output channel 3. Why 3 there? RGB, right? So in the beginning, you're getting those channels. After that, you're doing a reloop, right? Expectedly. Once again, you're doing a convolution, right? Second convolution is a very small network, basic one, with a 2x2 max pooling, etc., etc. And then the encoder block. So what is the encoder made up of? It is just made up of the blocks. Yeah. Block, channel in, channel out, blah, blah. Is this easy to understand, guys? Yeah. You do filter, follow it up with activation, follow it up with max pooling. You see this? Yeah. And this is your max pooling. And how do you do the forward? At each instance you apply, you put your input through the block, followed by pooling, isn't it? As simple as that. The only thing that you have to remember though is that you don't forget what you produce from each layer, because why? You will need it on the journey back up. Right? In the decoding part, you'll need to remember the journey. That is it.
It's more like a recursion.
Sort of, yeah. It's a so interesting way of doing it. And then that is your encoder. What will the decoder look like? Same thing is just transpose. Instead of conv, you will use transpose of the conv, isn't it? Do you realize that the code looks pretty much exactly the same? There's a little bit of cropping and mechanics here, but more or less, it's exactly the same. Yeah. But the important line is, look at this. You take these two things. You concatenate what? What you just produced from the previous decoding step, and you bring in what you saved from the encoder filters that it produced. You bring that in, and then you concatenate those, right? And then
Is that all that is there? Do you just concatenate to totally different vectors, and then that's it?
That's it. Yeah.
Oh my God.
Yes. See, neural networks, the magical thing is, much of the neural network is so dead simple, both in the coding, especially given PyTorch libraries, etc. You think logically and you write literally the code that is your logic. It's as simple as that. And then the amazing thing is the whole thing works. Right? And it not just works, it works amazingly well. These things work amazingly well. Right? And this is it. This is it. That's why they say unit in 60 lines. Somebody has written a blog, a very good thing. And the reason I'm asking you to read this code is it will demystify it for you. Right? You will literally see each line of the code as it happens, and you therefore become aware of image segmentation, which is an important task. Right? So guys, please go use it. And I want you guys to present, each team to present after lunch, their results of segmentation. Is that fair game? It's an easy exercise, guys. This is not a trick. It's a simple, easy exercise. Go do it.
Asif, a quick question. What will you be doing after lunch? Just presenting the results, or are we reading another paper?
Oh, we are going to read two more papers, Detter and Sam.
Okay.
Hey, Asif, we need some help. If Hamad is there, can he reboot the Cowboys machine? We lost access.
Which machine?
Cowboys.
Cowboys. Oh, you lost the Cowboys. Good grief. I'll reboot it. He's not here, but I'm going to reboot that machine for you.
Thanks.
And I know there's a long queue of people waiting for machines, the people who literally don't have machines and obviously don't have the bandwidth to purchase one. So I have good news. In the last 1 week, we built yet another 2 mighty servers. Each server has 128 threads, hardware threads, or hardware cores, and with this latest GPUs in them. Okay. We got another cache of GPUs yesterday from our provider supplier, and we put it into those machines. That's the good news. There's a bad news to it. I'm yet to power up the machine. I'll hopefully do it either in the lunch break or I'll do it today evening, but then I'll let those team know that are waiting for it. But those are really mighty machines, guys. And what the other part is that I've deliberately now put it in the data center behind me, so that it doesn't. One of the things I'm noticing is that the machines that are in the room, like for example, Prashant mentioning, this machine suddenly needs to be rebooted and lost connections, etc. So what happens is when it is sitting in the meeting rooms, it goes through human touch. People come, they touch, cables get shaken up and so forth. And so it's becoming unstable. So I'm now moving all the machines into the data center, because the machines that are in the data center and the teams that are using it, none of them are having any of these issues. Their uptime is much better. So you'll certainly see even if in your room there's a machine, you might see that it has disappeared like the Cheshire cat. So that's that. All right, guys. So with that, I'll end today. Please do this. Guys, please take it seriously. Have your teams do something, present it, because the next paper takes an entirely different approach. Right? And the paper after that takes an even more different approach. These represent great milestones in this field, guys, in computer vision. I've deliberately chosen only 3 papers. It's a vast field, right? But in this vast field, obviously in a day, how much can we cover in segmentation? I've deliberately picked 3 important milestones that we are going to do. So take it very seriously. Bring your fresh head. If you are feeling sleepy, go take a long walk and we'll meet you. So there we go.